Take a look at this single flame burning at the top of a coastal refinery stack. It's a small visual reminder of an overwhelming mathematical reality. Somewhere out on the ocean right now, a single floating steel structure is carrying up to 3 million barrels of crude oil. That is enough raw, combustible fuel to supply an entire country for a day, contained entirely within one hull. Most of the global shipping fleet hauls dry goods, piles of coal, holds full of grain, stacks of manufactured products. Those cargoes sit quietly in the dark, but tankers carry liquids. They transport dense, viscous black petroleum, deeply corrosive industrial acids, and highly explosive gases. And liquid does not stay still. If you put thousands of tons of fluid into a large open hold and send it into an ocean storm, the constant shifting momentum of all that weight crashing from side to side would quickly capsize the vessel. To survive those forces, the modern tanker cannot be built like a standard boat. It has to be engineered as a heavily fortified, leak-proof pressure vessel, designed entirely around preventing the catastrophic escape of its cargo. This internal cross-section shows exactly how that containment is achieved. Instead of one massive cavernous space, the inside of a tanker is subdivided. A grid of longitudinal and transverse steel bulkheads separates the hollow volume into dozens of smaller, isolated rooms. This solves what naval architects call the free surface effect. By breaking the liquid up into separate, sealed compartments, the diagram shows how those bulkheads act as physical brakes. They limit how far the fluid can travel, stopping the dangerous sloshing momentum before it can threaten the stability of the ship. That internal compartmentalization allows the ship to absorb and manipulate the immense kinetic energy generated by hauling bulk liquid across a turbulent ocean. While all tankers share that subdivided architecture, the fleet is split into 4 distinct families, and their specific engineering is dictated entirely by the physical state of the liquid they carry. This overhead view captures a very large crude carrier. The tugboats beside it look like toys, giving you a sense of its monumental scale. These vessels haul unrefined petroleum directly from the oil fields. When fully loaded, a VLCC can displace over 500,000 tons of water. Sitting so deep below the surface, they require specially dredged shipping lanes just to reach port. Contrast that sheer mass with the clinical precision of a liquefied natural gas carrier. These white domes are independent pressure tanks holding natural gas that has been cooled to minus 163 degrees Celsius. At that temperature, the gas shrinks to a fraction of its original size, becoming a liquid that can be shipped across the ocean. At minus 163 degrees Celsius, the cargo is so cold it would instantly destroy ordinary steel on contact. This animation illustrates the cryogenic solution. The liquid sits inside a primary membrane, surrounded by alternating layers of heavy thermal insulation and secondary barriers. The cargo never touches the actual structural hull of the ship. If cooling isn't the goal, shipbuilders use pressure. Liquefied petroleum gas carriers, transporting propane and butane, often rely on thick-walled steel cylinders on their decks, physically squeezing the gas into a liquid state through raw ambient pressure, defeating the heat, maintaining absolute cold, or resisting massive expansion. A tanker's primary job is to artificially freeze the physical state of nature for the duration of a voyage. Chemical tankers trade the massive scale of crude carriers for microscopic precision. While a crude tanker fills a few giant holes with a single product, a chemical tanker carries dozens of different highly refined industrial fluids simultaneously. You can see the result on the deck of this chemical carrier. Every single stainless steel tank requires its own dedicated pipe, pump, and valve system. If an industrial acid accidentally mixes with an organic solvent in the manifold, the resulting reaction could tear the ship apart. Absolute segregation of these chemicals is a survival requirement. Look at this dense arrangement of red pipework. Because liquid cargo can't be picked up with cranes or conveyor belts, it has to be pushed. Moving millions of gallons of product requires large electric centrifugal pumps deep in the hull, forcing the liquid up through these sealed deck pipes and out into the terminal connections. And as those tanks empty out, they fill with explosive hydrocarbon vapors left behind by the cargo. To prevent an accident, the ship pumps inert exhaust gas, or nitrogen, into the empty void, suffocating the space so fire physically cannot ignite. It is an entirely invisible, highly pressurized logistics operation. The liquid flows blindly through steel tubes, where turning just one single wrong valve on a standard loading checklist can quickly trigger a catastrophic chain reaction. A fire aboard a loaded tanker is one of the most dangerous maritime emergencies possible. Rigorous gas measurement, absolute static electricity control, and strict inerting procedures are the only things standing between a spark and an explosion. This archival image shows the grim reality of containment failure. When a hoe breaches and the primary pressure system gives way, the ocean is immediately choked by millions of gallons of toxic liquid, coating the water in crude oil. Disasters like the grounding of the Amoco Cadiz and later the Exxon Valdez laid bare the fragility of single-hull designs. The environmental devastation was so absolute that it forced international regulators to mandate a total structural overhaul of the global fleet. This animation demonstrates the result: the double hull. Every modern tanker is essentially a ship inside a ship. If the outer hull strikes a reef or collides with a pier, the empty void space absorbs the impact, leaving the inner cargo boundaries safely intact. Building two hulls takes thousands of tons of extra steel and hundreds of millions of dollars. But that immense engineering cost is the necessary premium for the secure delivery of the fuel and raw materials that keep industrial civilization operational. Ultimately, tankers are the invisible providers. They move crude oil that gets refined into jet fuel, the gas that heats cities in winter, and the chemicals that become fertilizers, medicines, and plastics. Energy alone is insufficient for global trade. Once that fuel powers the production of millions of consumer goods, the challenge shifts from moving liquids to moving discrete objects in a hyper-standardized system. That requires a very different kind of vessel, one that doesn't pump liquids, but instead stacks simple, standardized metal boxes high into the sky, acting as a floating warehouse for the modern world. Tankers carry the raw power required to build civilization, but the container ship is the tool that actually moves the world.